notepad? Yes or no?
Yeah, we can see it.
Okay, that's all you see.
Yeah.
Okay, good. Right. So this is week number 3. So week number 3, we're going to look at shear stress for thick wall. Okay, so we're going to look at thick wall shearing stress. Now this topic is one of the most confusing topic. I used to teach this towards the end of class or the end of term. I realize it's not a good idea. Let's do it now. And then I would like to announce term test 1 date is on June the 3rd, 6:30 to 10:30. So I'm giving you 2.5 hours to do the test, 1.5 hours to submit your answer online. Okay, so you have to take images, upload onto PDF. I'll give you more details later. Term test 2 will be on July the 8th and final exam August the 5th. How many questions? I don't know yet. It can be 2 or it can be 3 for now. I'll let you know probably next week regarding how many questions you will get. So term test 1 will be whatever we teach or I teach from the beginning of class, okay, from the first week up to the week before term test 1. Okay. Term test 2 will be whatever that I teach after term test 1 up to term test 2. And the final exam will be whatever I teach from term test 2 to the date of the final exam. I hope you get that clear. Okay, so but you still have to know what you learn in all the weeks. Okay, does not mean okay, it will not be tested up if we will forget. Okay, because the knowledge is accumulative. Right. So let's look at shearing stress. So shearing stress are acting parallel to the surface. Okay, so this is what you have to take note. It's not perpendicular. Perpendicular are the normal stress. Shearing stress are parallel to the surface. So if I were to draw a transformation now, so this is my X and this is my Y, and I'm going to construct an element. So we're going to draw an element. Okay, so this is my element. So what you see over here, shearing stress, it acts in this direction. Okay, so this is shearing stress. Right? Okay. So over here, you label the shearing stress and shear on the plane intersecting the x-axis, and the shear stress is acting in the y direction. Okay, so this x is the intersecting plane. This denote the shear stress direction. So if you look at this plane over here, okay, look at this plane over here that I'm drawing in green, right? It is intersecting the what? The x-axis. Okay, so that's why you put the first x, intersecting plane, so it's an x, and the shearing stress direction is going in the y direction. Okay, so likewise, to label this, the shear will be the plane, the intersecting plane is on the y-axis, and then the shear stress is in the what? X direction. Okay, so the intersecting plane, so this is the plane we are talking about in red. Okay, so it intersects the y-axis, and the direction of the shear stress is in the what? X direction. The other one, the direction of the shear stress is in the y direction. So for the state of equilibrium, okay, so for the state of equilibrium, we know that the shear XY must be equal to the shear YX. Always the case. Okay, always the case. So likewise, if you are to draw the full element, the other shear direction will go this way. Okay. And how how the element will deform is in this way. So the deformation pattern looks like this. So you pinch both ends. This is how the deformation pattern will deform. Okay. I will teach more on the deformation pattern later on when we do 2D and 3D Mohs circle. But this is just for you to know. Right. So now, if we were to go into 3D, so far, anyone, any questions, please? Well, okay. Okay. Oh, the question asks, when am I going to upload the question for quiz number 2 or quiz number 3? I'm going to upload them on Thursday evening or Friday morning. Okay, Thursday evening or Friday morning. Thank you.
Sir, can you explain the purple region again, please?
The what region? The
purple
purple.
highlight. Yeah.
Okay, so this arrow, so this one I've colored, right? Purple. I don't see purple. The pink, you mean?
Yeah, the pink, the pink.
Okay, the pink arrow over here, that is the shear stress direction. Does that make sense?
Yeah, okay, thanks.
Okay. So now,
I got a question.
Yep.
Sir, you wrote down state of equilibrium is equal to intersecting xy equals to intersecting yx.
Yep. No, the shear xy,
if
the shear xy is equal to the shear yx.
Yeah, does it matter if the shear xy is equals to shear xy, or is it always going to be shear xy is equal to shear yx?
Yeah, you flip it around, it's going to be the same.
Okay.
Okay. Does that answer your question? Okay.
Yeah.
So now if we go into a 3D configuration, okay, so this course I at the end of this course I want you to go into 3D. Okay, it's not just we are not in a 2D world, we're in 3D world, but learning fundamentals we look at 2D. So if we look at a 3D now, so this is your Y, X, Y, and then your Z, and then we have our element. Okay, so I'm going to sketch out our element. Right, so this is our element. Right, so as we have labeled the first one, right, where we've seen the first one, so this will be your shear, right? So this is a shear X plane intersecting Y direction shear stress. So this is the shear Y plane intersecting, the shear stress is in this direction. And then if I'm going to label the other side, so we are going to look at 2, 4. So this direction now. All right. So this is the shear acting on the plane X intersecting plane as in the what? Z direction. So the other side is shear Z, and this is X direction. And then the last one, yeah, the last one which I'm going to draw. Oops, sorry. Right, so this is shear intersecting plane Z in the Y direction, the shear stress in the Y direction. So the other side is a shear intersecting plane is the Y and it's acting in the Z direction. So for a 3D element now, right, in the 3D element, we have to satisfy 3 states of equilibrium. Is the shear in XY will be equal to a shear in YX. The shear in XZ must be equal to the shear in ZX, and the shear in YZ will be equal to shear in ZY. Okay, so that's for 3D. Now, let's look at how the structure will fail by shear deformation. Okay, so let's look at how the structure. So failure. by shear force induced deformation. Right. So if you have a cantilever beam, I'm just speaking an example of a cantilever beam. Okay, we have a cantilever beam. Okay, so one end is fixed, the other end is free, so it's built in, and then we have an applied force over here, right at the end, V, and then we're going to divide the beam. Okay, we're going to divide the beam into layers, right, into layers. So when the shear force at point B is applied, the structure will deform, right? The structure will deform. So I'm going to draw the structure that's deforming now. Okay, the structure that's deforming now. So again, built in. So over here, this is point A. So the structure will deform in this manner, right? It's going to deform in this manner. Okay, so I'm going to draw layer by layer again. So this is one layer. This is the next layer. This is the next layer. This is the next layer. And then I have one more layer to go. Right? Oh, my last one is pretty badly drawn. Try to make it better. Right. So this is how the structure is going to deform. So all this layer, what you see is you'll see a geometry that I've drawn down here. Right? And this is my delta. Right? That's my delta. Okay. So remember what I told you. Shearing stress is acting parallel to the surface. Okay. So I'm going to draw the transformation. So this is my X and this is my Y. And if I were to draw the element now, okay, we were to draw the element now. The element, so for example, the element I pick is the element at this end. Okay, so I'm going to draw the element. Now, if we were to incorporate the shear force is acting over here, V, right? And where we measure our delta, we measure our delta in this direction. And the shear stress is acting in this direction. Right? The shear stress is acting. So the shear stress is acting on the plane, right? So it's acting on the plane that I'm highlighting that is in yellow. But the delta is in the direction of the pink. Right? You can see this. Oh, so thick. Right? You can see the delta is measured parallel to the x-axis. The shear stress is acting parallel to the y-axis. Now, any questions so far? Do you all find this disturbing, yes or no? The shear stress is acting on the yellow surface, but the delta is on the what? On the pink colored surface. Anyone, any questions so far?
What is delta?
Delta means the change change in distance.
Oh, shear
Okay.
equal distance. Okay.
Okay. Because of the slip, your